Oxidation numbers. What are they used for? Why do you need to learn them? Two important applications for oxidation numbers. We use them to write chemical names and chemical formulas. Also to balance redox equations for analytical, organic, and inorganic chemistry. So what is an oxidation number? An oxidation number is a charge that is assigned to an ion or an atom. Now there are several cases to consider. The first case we'll look at is the oxidation number of elements, both monatomic like copper, silver, gold, etc., and polyatomic elements like dihydrogen, dichlorine, etc. The second case we'll look at is calculating the oxidation number in ionic compounds. And finally we'll look at the oxidation number in covalent compounds like hydrogen chloride and water, etc. First case, oxidation number of a monatomic atom. We will see that it's always equal to 0 because the total or net electric charge in an atom is 0. Let's look at the simplest atom, hydrogen, element number 1 on the periodic table. It has one proton positively charged in the nucleus and one electron negatively charged outside the nucleus. If you add these two charges together, they equal 0, and therefore the oxidation number of hydrogen is also 0. Let's consider the second element, helium. Helium is composed of 2 protons in the nucleus, 2 electrons outside. If you add these charges together, again, the total charge is 0, and therefore the oxidation number of helium is also 0. And this is true for all 118 monatomic atoms on the periodic table. They're all neutral. They all have an oxidation number equal to 0. Let's look at the oxidation number of a polyatomic element. We will see that that is also equal to 0 because, again, its atoms are neutral. Consider the diatomic hydrogen molecule H2. Here's the Lewis structure of the diatomic hydrogen molecule. Now the Lewis structure shows a line drawn between the 2 hydrogen atoms here, and that is a covalent bond made of 2 shared electrons here. Electrons are always shared equally between identical atoms. So to determine hydrogen's oxidation number, we divide the shared electrons, like so, giving 1 electron to each atom. So the hydrogen atom on the left owns, if you will, 1 electron, and the hydrogen atom on the right is assigned also 1 electron. And this produces 2 neutral atoms, each owning 1 electron. Each hydrogen atom is now the same as its Lewis symbol. Right there. Now, do you recall that Lewis symbols represent neutral atoms by showing 1 dot for each electron in the outermost shell, the valence shell of the atom? And since neutral hydrogen owns 1 electron, and this hydrogen atom owns 1 electron, we're going to say it is neutral, therefore its oxidation number will be 0. Like so. Let's look at a couple more cases. Diatomic oxygen, O2. Here's its Lewis symbol, or Lewis structure. It has 2 shared electron pairs, a double bond represented by 2 lines. Again, if we divide the shared electrons, giving each oxygen atom 2 electrons, we will produce 2 neutral oxygen atoms, each owning 6 valence electrons, like this. Count them with me. 2, 4, 5, and 6 electrons for the oxygen atom on the left, and again 6 electrons for the oxygen on the right. each oxygen atom is now the same as its Lewis symbol. Notice the Lewis symbol of oxygen owns 6 electrons and is neutral, and so do each of the atoms in the O2 molecule. And since the atoms of O2 are neutral, their oxidation number is 0. All right, one more time, let's consider the nitrogen molecule. Nitrogen molecule has a triple covalent bond. These 3 lines. If we divide those 6 electrons evenly between these 2 identical nitrogen atoms, then each nitrogen will have, or is assigned now, a total of 5 electrons. 1, 2, and then half of each bond, 3, 4, 5. And that is the same as a nitrogen atom's Lewis symbol, which owns 5 electrons and is neutral. And therefore, the oxidation number of nitrogen is 0. The same is true for all the polyatomic elements: tetraphosphorus, octasulfur, dichlorine, difluorine, dibromine, diiodine. All their atoms have an oxidation number equal to 0. Okay, how about ionic compounds? Very simple. The oxidation number of an ion is the same as its electric charge. So look at the Lewis structure of calcium chloride. Now, calcium chloride is an ionic compound. It's made of 1 calcium cation, Ca+2, and 2 chloride anions, Cl-. The oxidation number of the calcium +2 cation in calcium chloride is exactly the same as its charge, +2. The oxidation number of the chloride anion in calcium chloride is the same as its charge, -1. Pretty simple, right? All right, here's a practice one for you. State the oxidation number of both atoms in aluminum oxide. Here's the structure of aluminum oxide. We break it apart into its ions. Aluminum oxide contains 2 Al+3 cations and 3 oxide -2 anions. So, since aluminum oxide is an ionic compound, the oxidation numbers of the Al+3 ion and the oxide -2 ions are the same as their electric charges, +3 and -2 respectively. Finally, calculating the oxidation number of atoms in a covalent compound. Now, by definition, compounds are made of different types of atoms. Here are 3 structures. On the left, we have sodium chloride. It's an ionic compound. It doesn't share any electrons. In the middle, we have hydrogen chloride. It's a polar covalent compound. This shared pair of electrons is not shared equally because we have different atoms sharing them. And finally, on the right, we have chlorine, a nonpolar covalent molecule. This shared pair of electrons will be shared equally because the atoms are identical. Now, unlike ionic compounds such as sodium chloride that contain charges, the covalent compounds like HCl and covalent molecules like chlorine, notice they don't contain any ions. In Cl2, chlorine, these bonded electrons are shared equally. Now, bonded electrons are not stationary. They're traveling approximately 1/10 the speed of light, and they are represented by this cloud as the electrons move around. Notice the cloud is symmetrical because the chlorine atoms share the 2 electrons equally. Look at the electron cloud in HCl. Notice how it's distorted. The electrons here spend most of their time around the more electronegative chlorine. And I'm going to state that again here. In HCl, the shared electrons spend most of their time around chlorine, indicated by the larger electron cloud, around chlorine, and they spend less time around hydrogen, indicated by the smaller electron cloud. So we need to talk about electronegativities. This is Linus Pauling's table of electronegativities. More electronegative atoms, those with the higher electronegativity value, hold electrons more strongly than the less electronegative atoms. So if you're familiar with the periodic table, you know that the nonmetals on the top right of the periodic table are more electronegative. They tend to hold their electrons strongly and even tend to take electrons away from metals on the left, which hold their electrons loosely. So how do we calculate the oxidation number of atoms in covalent compounds? Let's look further. To do this, important rule, all shared electrons in covalent bonds are assigned to the more electronegative atom, and they're taken away from the less electronegative atom. Let's consider HCl a little further. Since chlorine, electronegativity 3.0, is more electronegative than hydrogen, electronegative 2.1, we assign both shared electrons in this pair, this bonded pair, we're going to assign them to chlorine, which is more electronegative. And therefore, we're going to ascribe all 8 valence electrons in this structure to chlorine, giving chlorine 1 more electron than the neutral atom has in the Lewis symbol. So here is the Lewis symbol of chlorine, and it's neutral. When it's neutral, it owns 7 electrons. But in HCl, we're assigning it 8 electrons. 1 more electron than the neutral atom means that chlorine in HCl has an oxidation number of -1. And this leaves hydrogen in the structure without any electrons, 1 less electron than the Lewis symbol. Again, this is a neutral atom of hydrogen owning 1 electron. This has none. Therefore, the oxidation number of hydrogen in HCl must be +1. Be careful here. There are no ions actually present in HCl. It is not an ionic compound. In these cases, the oxidation number does not represent the electric charge. We'll summarize this at the end to clarify. Let's go further. Look at the Lewis symbol. Look at the Lewis structure of a water molecule. Let's look at the Lewis structure of a water molecule. Oxygen has 2 unshared non-bonded electrons right there. The non-bonded electrons belong entirely to the oxygen atom. They're not being shared. There are also 2 shared pairs of electrons, the covalently bonded electrons, right there. These 4 bonded electrons are not shared equally. They spend more time around oxygen because oxygen is more electronegative than hydrogen. So all 8 valence electrons will be assigned to oxygen when calculating its oxidation number. Thus, oxygen is assigned 8 electrons, and hydrogen is not assigned any electrons. Each hydrogen in water has 1 less electron than its Lewis symbol, shown here, and therefore hydrogen is assigned an oxidation number of +1. The oxygen in water has 2 more electrons. It has 8 electrons instead of 6 electrons like the neutral oxygen atom's Lewis symbol, and therefore oxygen is assigned an oxidation number of -2. Note that in almost all of its compounds, oxygen has an oxidation number of -2. So here, notice here that hydrogen and oxygen are not truly charged. Hydrogen is not a +1 cation, oxygen is not a -2 anion, but these are simply assigned charges. They are oxidation states. And we only do this to calculate the oxidation number. Let's take a look at peroxides. Peroxides are an exception to the oxygen rule that oxygen is always -2. The per in peroxide tells us that there's one more oxygen in the formula than is normally present. Hydrogen peroxide, H2O2, is a simple example of a peroxide. The oxygen atoms in peroxides have an oxidation number of -1 instead of -2 because they're assigned 7 electrons instead of 8. Now they only have one more electron than a neutral atom. So count with me the electrons that the oxygen on the left owns. 2, 4. Both of the electrons that are being shared are assigned to oxygen since oxygen is more electronegative than hydrogen. But on the right side, we can only assign one electron to each oxygen because they equally share the pair. 2, 4, 6, and 1 is 7 electrons assigned to oxygen. Therefore, its oxidation number is -1. Now, hydrogen can have oxidation numbers equal to -1 as well as +1. When would this happen? Well, when hydrogen is bonded to a less electronegative element, such as a reactive metal. Lithium hydride, LiH, is an example. This is the Lewis structure of lithium hydride. It truly is an ionic compound with a hydride anion. In lithium hydride, notice the hydrogen owns one more electron than its Lewis symbol. The Lewis symbol would be 1 dot. It's in group 1a. But since it owns 2 electrons, it has an oxidation number of -1 here. Note also that the IDE ending in hydride indicates that hydrogen is the more electronegative atom and is named as an anion, which in this case it truly is a charged anion. So now that you understand how oxidation numbers are determined, you can relax in the knowledge that you don't have to draw Lewis structures every time you need to find an oxidation number. There's a simple method for learning oxidation numbers. It will require a little bit of memory and a little understanding of the periodic table. The group 1a metals, lithium, sodium, potassium, rubidium, cesium, francium, their oxidation numbers are always +1. They only have one valence electron, and they lose it in all their reactions, gaining a +1 charge, and therefore their oxidation number is always +1. And so is silver, by the way. Silver is in group 1b. What about the group 2a metals? Well, they all have 2 valence electrons, and they always lose them in all their reactions, and therefore they obtain an oxidation number of +2 in all cases. And by the way, so are zinc and cadmium, always +2 oxidation state, and they're in group 2b. The group 3a elements, at least the upper end of group 3a, boron, aluminum, and gallium, always have an oxidation number of +3. Do you remember that the group 1a metals, the A group metals, do you recall that the A group metals tend to lose all their valence electrons to become isoelectronic with the nearest noble gas? So if you know the group number of an A group metal, you usually know its oxidation number. Let's continue. In group 7a, fluorine always has an oxidation number of -1. This is because it's the most electronegative element on the periodic table. It will always be assigned any electron that it shares. Now the other halogens, chlorine, bromine, iodine, may have positive oxidation numbers, but they will always be -1 when the halogen is the more electronegative atom in the compound. Here's some examples to illustrate. In HCl, chlorine is more electronegative than hydrogen, so chlorine will use its -1 oxidation state only. In sodium bromide, bromine is more electronegative than sodium, and so bromine will only have an oxidation state of -1. In potassium iodide, iodine is more electronegative than potassium, and therefore iodine will have a -1 oxidation state. So in all these compounds, chlorine, bromine, and iodine are in their -1 oxidation states because they are the more electronegative atom in the compound. What about group 6A? We know that oxygen is virtually always -2, except in peroxides. The other group 6A chalcogens, sulfur, selenium, tellurium, they will also have an oxidation number of -2 when they are the more electronegative atom in the compound. For example, in hydrogen sulfide, sulfur is more electronegative than hydrogen. Therefore, it uses its -2 oxidation state. And what about group 5A, the nicogens? The group 5A atoms will always have an oxidation number of -3 when they are the more electronegative element in the compound. For example, in ammonia, nitrogen is more electronegative than hydrogen, so it will use its negative oxidation state, which has to be -3. Gaining 3 electrons makes it isoelectronic with the nearest noble gas. So recall that the A group nonmetals tend to gain enough electrons to fill their valence shell to become isoelectronic with the nearest noble gas. So here is a listing of the elements with fixed oxidation numbers. You need to memorize these. It will take very little memory, maybe only 1 or 2 bytes on the hard drive, if you understand it. Let's review. Group 1A metals, lithium, sodium, potassium, rubidium, cesium, francium, always +1 in all their compounds because they're in group 1A. The group 2A metals typically lose 2 electrons, no exceptions. Therefore, they form +2 cations and are +2 in their oxidation states. Recall also zinc and cadmium in group 2B are always +2. In group 3A, boron, aluminum, and gallium, always +3 oxidation state. What about the nonmetals? Fluorine is always -1. It's the most electronegative element. The halogens, in general, chlorine, bromine, iodine, will always be -1 when they are the more electronegative atom in a compound. They like to gain 1 electron to become like a group 8A element. By gaining 1 electron, they have an oxidation state of -1. What about group 6A? We discussed oxygen, always -2, except in peroxides. The other group 6A chalcogens, -2 whenever they are the more electronegative element in the compound. Group 6A elements wish to gain 2 electrons to become like group 8A. Group 5A elements, nitrogen, phosphorus, arsenic, antimony, yes, they can have positive oxidation states, but when they are the more electronegative element in the compound, they will always be -3, arguably gaining 3 electrons to become isoelectronic with the nearest noble gas. And let's take a look at hydrogen. Remember, it is normally +1 when combined with a more electronegative atom, but when it's combined with a less electronegative atom, then it takes its negative oxidation state. So atoms with fixed oxidation numbers are shown. Metals cannot have negative oxidation numbers. They would never gain electrons. The nonmetals can have negative or positive oxidation numbers. Look at iodine monochloride. In this compound, chlorine is -1 because it's more electronegative than iodine, but compare chlorine monofluoride. The oxidation state of chlorine is now +1 because it's combined with more electronegative fluorine, which of course is -1. Note that the nonmetals with higher electronegativities in compounds will always use their negative oxidation state. Now this is easy to remember. Again, Group 7A needs 1 electron, hence -1 to be like group 8A. Group 6A elements need 2 electrons, hence -2 oxidation states to be like group 8A. Group 5A elements need 3 electrons to be like group 8A, hence -3 oxidation states. Put it on the hard drive. Memorize those numbers. Once you memorize the oxidation numbers of the elements that have fixed oxidation numbers, all the other oxidation numbers are calculated from the chemical formula. So here's an important rule. The sum of the oxidation numbers in a formula will be equal to the total charge on the formula. Add up all the oxidation numbers, they have to equal the total charge in the formula. Let's look at some examples. This is hydroxide ion. Notice the charge on hydroxide is -1 in the top right corner, and therefore the sum of the oxidation numbers of oxygen and hydrogen have to equal -1. And sure enough, they do. Oxygen we know is -2. Hydrogen, being less electronegative, will be given +1. These add to be -1. Here's water. Now water has a charge of 0. We don't normally write, in fact we never write, a charge of 0 beside a formula. It's understood. Since the total charge is 0, the sum of the oxidation numbers of oxygen and hydrogen must also be 0. And there they are. Oxygen is -2, each hydrogen is +1. The sum must be 0. Now this is the ammonium cation, NH4+. The charge on ammonium is +1. And so the sum of all the oxidation numbers within it must add up to be -1. There are 4 hydrogens. Being less electronegative than nitrogen, they take their +1 oxidation state. That leaves nitrogen with an oxidation state of -3, +4, makes +1. Nitrogen being in group 5A, we'd predict its negative oxidation state is -3. Now you want to be careful here. The oxidation state of -3 for nitrogen is not the same as its actual charge. The actual charge on nitrogen is +1 because it only truly owns half of what it shares. It owns 4 electrons instead of 5. But in terms of calculating the oxidation number or state of nitrogen, we assign it all 8 electrons because it's more electronegative, giving it an oxidation number of -3. So be careful, oxidation number is not necessarily the same as actual charge, and we will summarize this at the end of this presentation. All right, let's do some examples. Calculate the oxidation number of a manganese atom in MnO2. The process is that we're going to use the known oxidation number of oxygen to calculate the unknown oxidation number of manganese. Here I've laid it out for you. Follow with me if you would. I'm saying the oxidation number of oxygen is -2, and we multiply this by 2 because there are 2 oxygen atoms in the formula. So -2 times 2 is -4. That's the total negative charge for the oxygen anions. Now, since the formula shows no charge, see the invisible 0 up here? Chemists, you have to get used to seeing the invisible 0. Because of that, you know it's neutral, and this means that the manganese atom must have an oxidation number of +4 such that the total positive and negative charge equals 0. Now, it's helpful for you to think of this as a math equation, if you like. We're going to say manganese, we're going to solve for the oxidation number of manganese plus a -4 for the 2 oxygens must equal 0. Rearranging this equation, we find that manganese is +4. This compound is therefore named manganese 4 oxide, where 4 is the Roman numeral 1V. This compound is named manganese 4 oxide, where 4 is the oxidation number of manganese in Roman numerals. You see, manganese has actually 5 different oxidation states. If you were asked, pass the manganese oxide, your next response will be, which one do you want? There are 5 different formulas of manganese oxide. We need to state which one it is. And that's the rule. The oxidation number of an atom is stated in a name only when the atom has more than one oxidation number. For example, you would never say pass the sodium 1 chloride, because sodium only has one oxidation state, so it's not stated. All right, let's do an example. Calculate the oxidation number of the manganese atom in MnO2. The process is we're going to use the known oxidation number of oxygen to calculate the unknown oxidation number of manganese. Here I've laid it out. Here's the process we'll follow. We're going to multiply All right, let's calculate the oxidation number of manganese in MnO2. The process is we will use the oxidation number of oxygen to calculate the unknown oxidation number of manganese. Here I've laid it out. We're saying calculate the oxidation number of manganese, and we're going to fill in the known oxidation numbers. So the oxidation number of oxygen is -2. We multiply this by 2 to get -4 because there are 2 oxygen atoms in the formula. So the total negative charge is -4. The total charge in the compound is 0. Chemists, you must begin to recognize the invisible zeros on formulas. The sum of all the oxidation numbers must equal 0. And therefore, the oxidation number of manganese must be +4 such that they all add to 0. Now when you're first doing this, it's helpful to think of this as a math equation. The sum of all the oxidation numbers equals the total formula charge. So here I've written the unknown oxidation number of manganese -4 equals 0. You can rearrange and solve and say that manganese is +4. And therefore, this compound is named manganese 4 oxide, where 4 is the oxidation number of manganese, and it's written in Roman numerals. Now, it turns out that manganese has actually 5 different oxidation states, and there are therefore 5 different oxides of manganese. If you were asked, pass the manganese oxide, your response would be, which one? Because there are 5 possible formulas, 5 different compounds. So, the oxidation number of an atom is stated in a name whenever the atom has more than one oxidation number. This is one case. Let's look at a second example. Find the oxidation number of manganese in Mn2O7. Once again, notice the total charge must equal the invisible 0. The process is we use the known oxidation number of oxygen to calculate the unknown oxidation number of manganese. Here I've laid it out again. We're going to multiply the oxidation number of -2 for oxygen times 7, because the formula tells us there are 7 oxygen atoms. 7 times -2 is -14 is the total negative charge. Therefore, the total positive charge must be +14 so that it adds to 0. +14 divided by 2, because there are 2 manganese atoms, gives us the oxidation number of each manganese atom. We always report the oxidation number of a single atom. In the same way that you multiply the -2 charge of one oxygen by 7 to get a total charge of -14, you would then take the total positive charge and divide it by the number of manganese atoms to find the oxidation number of an individual manganese atom, +7. Again, here's a math equation to represent that. 2 times the oxidation number of manganese -14 for the 7 oxygens equals 0. Rearranging this equation, you find that manganese is +7. And therefore, the name of this compound will be manganese 7 oxide, where 7 is the oxidation number of manganese in Roman numerals. All right, here's some practice for you. I'm going to run through these reasonably fast, and you can just stop the video if you need to pause and do the calculations ahead of time. N2O. nitrous oxide, by the way. We're going to say 2 times the oxidation number of nitrogen, subtract 2 for the 1 oxygen equals the total charge of 0. Rearranging this, you find that nitrogen has a charge of +1. How about dinitrogen pentoxide? We'll write an equation saying 2 times the oxidation number of nitrogen minus 10 for the 5 oxygens equals 0 charge. Solving for the charge on nitrogen, you find it's +5. This is the sulfite anion. I'm going to write a formula that says the oxidation number of sulfur minus 6 for the 3 electrons equals the charge on the complex compound, -2. Solving for sulfur, we see it's +4. Cadmium bromate is next. Now, cadmium is one of the elements that has a fixed oxidation number. It's always +2. So I'm going to write that in as +2 for cadmium, plus 2 times bromate in the brackets. Now notice there's a 2 after the bromate. That's the chemical way of multiplying a group. In math, we put the 2 in front, but in either case, it means 2 times whatever's in the brackets. Bromine is what we want to solve for. -6 is for the 3 oxygens, and that must equal 0, the total charge. If I rearrange the equation, I find that bromine is +5. Here's a simple one. I can say the oxidation number of silicon, -4, subtract 4 for the 4 fluorides equals 0, and therefore silicon is +4. This is sodium chromate. Sodium has a fixed oxidation number of +1. So I can write 2 for the 2 sodiums, plus the oxidation number of chromium, minus 8 for the 4 oxygens equals 0, the charge on sodium chromate. Rearranging for chromium, I find that it is +6. Here's P2O7 minus 4. For this I can write 2 times the oxidation number of phosphorus, subtract 14 for the 7 oxygens equals the charge of -4. Rearranging and solving for phosphorus, you find that phosphorus is +5 oxidation state. Next we have bicarbonate. Note that in this compound, hydrogen is the least electronegative element. It will use its positive oxidation state of +1. So I would write +1 for the hydrogen, plus the oxidation state of carbon, minus 6 for the 3 oxygens, equals -1 total charge. Rearranging for carbon, I find its oxidation number is +4. Next we have Cr2s3. I can write 2 times chromium's oxidation number plus 3 times the charge of a sulfide. Now, sulfur is more electronegative than chromium. It will use its negative oxidation number. It's in group 6A, so it's -2 like oxygen. Rearranging and solving for chromium, I find that chromium is +3 oxidation state in this compound. Hence, this compound is named chromium 3 sulfide. And finally, Fe3P2. Phosphorus is in group 5A. It's more electronegative than iron. It will use its negative oxidation state. A group 5A element wants to gain 3 electrons. It'll be -3. So I'm going to write 3 times the oxidation state of iron plus 2 times the -3 for the phosphide equals 0, the charge on the compound. Rearranging for iron, I find that iron is +2, and therefore the name of this compound is iron 2 phosphide. So here's a summary of what we've seen. Monatomic elements, copper, aluminum, zinc, gold, silver, etc., they have an electric charge of 0. They have no charge, they're neutral, and their oxidation number is 0. The polyatomic elements, dihydrogen, dioxygen, tetraphosphorus, octasulfur, etc., their electric charge is also 0. Their oxidation number is also 0. Ionic compounds, sodium chloride, calcium chloride, aluminum oxide. Now the charge varies. It's never equal to 0 because they're ionic, they have charges. The oxidation number is simply equal to whatever the ion charge is. And finally, covalent compounds like HCl, carbon dioxide, hydrogen sulfide, etc., well, they have no charges in them. they're not ionic. In these compounds, the shared electrons, the bonded electrons, are assigned to the more electronegative atom. The oxidation number is not equal to the charge because no charges are present. You simply have to calculate them. So here is a table showing most of the elements and the most common oxidation numbers. Here we have the ones we've learned, those with fixed oxidation numbers, and then other ones that have multiple oxidation states. Now it's helpful to know that iron, for example, can be only 2 or 3, and cobalt and nickel likewise. It's helpful because when you have to calculate it, it narrows it down to just 2 possibilities. You got a 50% chance of getting it right. This is not something you have to memorize, but you'll find that as you go on in chemistry and study more, you become more familiar with it. It gets so easy, it's just a matter of course. Well, I hope this has been helpful. I hope you have an understanding of oxidation numbers. Once you grasp this, it should make your chemistry experience a lot more pleasurable.